Hi, welcome. I am Dayanidhi and this is my journey through ENPM 701 Autonomous Robotics. In this course, we designed, built, and programmed a ground robot to simulate constructing a shelter on Mars by collecting colored blocks scattered across a cluttered terrain and delivering them to a designated construction zone. As you can see, this was the robot that we built, and this one is the power bank that is powering the Raspberry Pi, and this is the LD L289N motor driver, and this is the ultrasonic sensor and the Pi camera. This is the gripper, which is controlled by servo motor, and all these wheels are connected to the DC motors, and the right rear wheel and the front left wheel is connected to a optical encoder which connects the ticks of the rotation of the motor. So once this is done, we further added a safety switch to cut off supply from the batteries to the motor driver. In case of an emergency, if it is placed on a table or something, it shouldn't fall over or fall off. These were the three blocks that were given to each of the students who were trying to complete this project. So each block were supposed to be picked in an order: red, green, and blue. And this was denoted as the construction items, and this was supposed to be kept inside the or placed inside the construction zone once picked from the scattered area. In this video, I'll be covering hardware and software aspects of this project and Grand Challenge overview. First, we'll begin with the hardware design. Our platform began with a pre-built chassis kit, which had frame, motors, wheels, motor drivers, Raspberry Pi camera, ultrasonic sensors, and a servo gripper assembly. We then added locomotion by adding the magnetic encoder onto the motors, and then we were supposed to start this assembly from scratch, and we had to put together all the screws, nuts, and all the wires together to make it as one fully functional robot. In this process, we were able to cover perception, gripper, and compute and power the Raspberry Pi. We also had an opportunity to solder the IMU sensor and connect it with the Arduino Nano and gather IMU data in real time. And that real time IMU data was used to gather the robot's orientation, and later we were able to use that IMU data and integrate encoder value to get the localization of the robot. Next, we'll move on to the software architecture. Our code base consisted of modular Python scripts, low-level motor control via RPI GPIO library, encoder reading with interrupts, ultrasonic sensor was used to detect the obstacles, and the OpenCV was used to detect the blocks and also to calculate the distance and move around the Grand Challenge arena. So, to give an overview on Grand Challenge, we'll first begin with the rules and specifications for the Grand Challenge. The robot should have the base mobile platform, and each of those robots should have motor driver, motors, frames, Raspberry Pi camera, ultrasonic sensor, servo gripper assembly, and only one robot may perform at a time, and each student must construct their own robot. Each robot must have a safety shutdown switch, which I explained at the start. And students must communicate with their robot wirelessly via Wi Fi and start the robot during the grand challenge. The testing area was 12 by 12 feet in square, and in that 4 by 4 feet square feet were the construction zone, and 2 by 2 feet was the starting zone, and remaining all the empty space was the cluttered environment where all the blocks were placed to be picked and placed inside the construction zone. In the next phase, we had to integrate, test, and calibrate the software architecture that we built and the modular Python scripts that were used to perform certain or particular tasks that were given as an assignment throughout the semester. In this phase, I was able to integrate encoder and IMU sensor values to get the exact localization of the robot, which was essential for me to determine the exact location during the grand challenge to perform certain tasks. And moreover, I was able to integrate ultrasonic sensor to determine how far the obstacle is, and based on the distance, I was able to perform an operation to avoid hitting the obstacle. Throughout the semester, I faced several obstacles. In those, major three obstacles were the false positive in color detection under class lighting. This was resolved by changing the HSV color space to a dynamically thresholding to red, green, and blue specific values. And next it was the gripper jitters, which used to give trouble while picking up the block or placing the block in a designated location. The unresolved major obstacle was the odometry drift, which was the major reason that I couldn't complete the grand challenge during the final run. During the practice runs, my robot successfully grasped each block, but during the official grand challenge, it failed catastrophically. The failure stemmed from accumulated odometry drift, compounded by low battery voltage causing slower turn rates, and which caused a perfect storm. Here's the map of block locations from our Grand Challenge arena. I was able to earn 3 points during the practice run. Unfortunately, during the official run, I was not able to perform as well as during the practice run. From the challenges I faced throughout this semester, I was able to grow certain skills and learn certain lessons such as mechanical integrations, to precisely assemble, and software engineering to build a modular code and use real-time OpenCV. Next one was the systems thinking, which is balancing hardware limits with algorithmic robustness. Last but not the least, project management, which was essential to maintain the documentation of the project and also allot certain time and certain tasks in priority to complete this project. Finally, by ending with a positive outlook, while the grand challenge didn't go as planned, failure is a powerful teacher. Moving forward, I'll implement real time battery voltage monitoring with automated slowdown mitigation. Along with that, higher torque servos for more reliable movement of the robot and also to get more precise localization. Finally, thank you so much for sticking till the end of this video. I hope you like it, and